Chapter 11, Limit and Introduction to Calculus. So Chapter 11 is dedicated to introduce the basic concept of limits and calculus, including derivative and integral. So especially first subchapter of chapter 11 is just showing that basic idea of how limit works for defining the extreme case of the numbers. So we're going to start with the definition of a limit as first part of the chapter 11.1 and just get used to that idea by solving some example problems. So chapter 11.1 is concept of limit. As first part of this chapter 11.1, we have to just check how the limit is defined in terms of the basic function describing that the x, y, z coordinates. So let me just write it down. The definition of a limit. So normally limit is defined with this description. If function fx becomes arbitrarily close to a unique number L as x approaches C from either side, the limit of function fx as x approaches C is L. So this could be actually expressed with the symbol of a limit. So if you use the basic symbol of limit, then that should be limit x approaches C, fx is L. So this is easy way to define the concept of the limit with the constant values L. So let's take a look at the basic concept of limit with the example problems. So let's just bring up some example function. fx now is 3x minus 2. Then now if limit case of x approaches to 2 of this function fx, then that should be limit x approaches to 3x minus 2. So now if the number of x goes to and getting close to number 2, you will see how that fx, the limit case of the fx actually becomes what number. So now let's set up the table. I'm going to list x values from the lowest number to the highest number. I'm just like randomly pick up the numbers, but with some range of scale. So let's just start with 1.9 in x, and that's move to 1.99 and 1.999 and 2, then gradually getting bigger and bigger. That's 2.001, 2.01, and 2.1. So with that numbers, fx becomes, for example, 1.9 of x, that makes this fx is 3.7. 1.99 makes this fx 3.97. 1.999 of x make this fx 3.997. And 2, if you plug that into the fx, then that becomes 4. And 2.001 make fx 4.003. 2.01 make fx 4.03. 2.1 makes fx is 4.3. So you can see the trade-off of the fx in terms of the x value. So as fx becomes bigger and bigger and approach the number 2, and you can see fx becomes bigger and bigger and getting close to number 4. Once you pass through the number 2 of x value, then fx becomes bigger, and that difference between the adjacent number and number 2 becomes bigger and bigger too. So depending on the where you're looking at, which direction you're looking at, as x approach the number 2, then fx also approaches number 4 from minus negative direction and positive direction. So x value can get into the number 2. This fx becomes closer to the number 4. So as you can see, if set up with the limit case with the x with the number 2, then fx becomes number 4 based on this given function. So there's some cases limit doesn't work. So we're gonna take a look at the case that the limit failed to exist. So for example, let's take a look at function with absolute value. So this is example, limit of x approaches 0 for absolute x of x. So if you plot this x, there's 2 different numbers possibly existing. If x becomes large, the positive number, then absolute x of x equals x over x, which is 1. But if smaller than 0, there's a negative value, then absolute value x of x becomes minus x over x, so that is minus 1. So if you plot this one, then that should be like this. This is x, this is y, this is fx. So if it comes from positive x to 0, then this fx becomes plus 1. If it comes from negative values of x to the 0, then that is minus 1. So this area, these numbers at x equals 0 is discontinued. So in this case, that you'd not be able to actually define limit case, because depending on which direction you're looking at, that function absolute x over x becomes plus positive 1 or negative 1. So there's no way to define this value of limit case. Another example might be possibly. Let me show you another example. Let's take a look at the inverse power function of x. So basically, if the function fx is proportional to the 1 of x squared, then if you plot that, then the value of fx diverges when x equals 0. You see that from this graph. So if you take limit case of x goes to 0, for the fx, the 1 over x squared, then as you can see, the x of x goes to infinity. So that doesn't also, this limit of function fx does not have solution. All right. Let's take a look at some properties of limits. Okay. So let me clear up this page. Okay. Okay, let me just reopen it. Okay, so let's take a look at some properties of limits. I'll just take it off first. So, I need to change the color of pen first. So, the property of the limits. So basically, if x goes to c in the limit with the function fx, then that value of that limit case is same as the fx with x is c. So if you plug the c into the in this function fx to replace x with the c, then that is the solution of this limit of fx in case the x goes to c. So let me show you the basic limit case, basic property of limit. Number one, if x limit b for x goes to c, then that is the same as c. So if you have constant value inside the limit, then that doesn't change property of limit. So it should be same as just constant value of b. So number two, limit of x for x goes to c, then that is the limit x for x goes to c, then the solution of that case is c. Just all you need is plug the c into the x. Number three, if you have power function, polynomial function inside of this limit, then that should be same as c to the power of n. So basically all you need is just replace x with a c if x goes to a c. Number four, limit of x to the power of 1 of n. In case x goes to c, then same thing, need to plug the c into the x function of fx. So that has the answer and the solution of n square root of c. Let's take a look at the property of the limit again. So properties of limit. So the limit of x is equal L in case x goes to C, and limit function gx for x goes to C equals K. Then number one, scalar multiple. If the function fx is multiplied by constant scalar number b in the limit like this, and that goes to C, then that should be just b times L, because b can that should be b actually, because b can be out of this limit, so that could be first taken out of this bracket. So if you take the b out of it, then that's just same as b times limit of function fx for c goes to x goes to c. So this one is L, so that should be b times L. Next, sum or difference. Number two, sum or difference. If the function inside of its limit with the fx and gx, then this limit could be applied to the fx and gx separately. So limit can go into the first term and the second term. So that could be re-expressed with the limit function fx, x goes to c plus minus limit of gx, and x goes to c. Here, limit fx is L, and this limit gx is k. So that could be L plus minus k. Okay, and the product, number three, product. The inside of the limit consists of fx and gx and their multiplication or their product, like this. Fx and gx, x goes to c. Then, just like sum or difference case, that limit can be split into the fx and gx separately. So you can actually re-express with the limit of fx times limit of gx for c. So this one is L, this one is k. So that should be L times k. Okay, that is product rule. And number four, quotient rule. Same thing, same thing like the product rule. So that limit fx over gx. So that limit can be applied to numerator and denominator separately. So this one could be limit fx, x goes to c, and the limit gx, x goes to c. So the numerator and denominator could be expressed with the L and K. So that should be L over K. Here K should not be same as 0. Otherwise, if k goes to 0 or k is 0, then that make this value goes infinity. Number 5, power rule. So that is limit fx to the power of n for x goes to c, then that should be, that limit can be plugged into the n's power. So that is same as limit fx x goes to c to the power of n. So inside of this bracket is same as L. So the result is L to the power of n. That's the properties of the limits, and we gotta just move on to the next properties of the limit with the polynomial and rational functions. Let's take a look at it, and we'll just find just an example to use that properties to solve the problem. Okay. Next one, we want to actually check the limit of polynomial and rational functions. So, next one, hold on. Okay. All right. I just deleted it. Okay, so here, the limit of polynomial and rational function. So what you need is just replace fx with the polynomial function px and find out how that px expressed in case that x goes to some finite number c, and also we'll find out how rational functions with the polynomial function at px and the gx can be expressed in case the x goes to some finite number c. So if the fx is function of polynomial function like this, the limit of that kind of function in case the c goes to, x goes to c, then you just need to replace x with a c. And number 2, if there's rational function inside the limit, which is expressed with the px and gx, here g x is c is not equal value. So otherwise gx becomes 0, then they make this rx function goes to infinity, so there's no solution. And now if you find that the value of rx in the case x goes to c, then that should be same as rx, but with the x is c. So you replace x with a c, then the limit of that rx should be rc. And now rx is the px over gx, so if fully expressed, then x should be replaced with the c. Same thing for denominator, x should be replaced with a c. So that should be fc over gc. That is genetic solution for rational functions. So let's take a look at example problem to find out how those rules work in case that the fx function is either rational function or polynomial function. So example number 10. We want to find out the limit of fx, which is x squared plus x minus 6, in case that x goes to minus 1. So you plug that into the formula, then that should be minus 1 squared plus minus 1 minus 6. So that should be 1 plus 1. I'm sorry, that's actually 1 minus 1 minus 6. So that will lead to the minus 6. And now you want to actually look at limit case of rational function. So the function is defined by x squared plus x minus 6 over x plus 3. For the case x goes to minus 1. So now you plug the minus 1 into this formula, then that should be minus 1 squared plus minus 1 minus 6 divided by x plus 3. Here x is minus 1, right? So that is minus 1 squared plus minus 1 minus 6 and minus 1 plus 3 over. So this one, as I said, x1 minus 1 squared plus minus 1 equals 0. And now the denominator is 2, and the numerator is minus 6. So the answer is minus 3 for example number 10. So let's move on. Next topic in this chapter is to set up to find that some techniques for evaluating the limits. So we will go through some basic technique to find out the value out of the limit for some functions. So the first technique is dividing out technique. So that is number one technique to evaluate the limits in some condition. So chapter 11.2 techniques. For evaluating limit. The first technique is dividing out our technique. So let's just solve example number one to find out how to use that dividing out technique. So example number one. Example problem number one. So that is, there is a function, rational function is x squared plus x minus 6 over x plus 3. And we want to find the value out of that function in case the x goes to number 3. So that is limit of x squared plus x minus 6 over x plus 3 for the x goes to minus 3. So now we got to do some rearrangement numerator. So if you just reset like a numerator with the variable separation, then that should be x plus 3 times x minus 3. And there's same type of term in the denominator too. So x plus 3 could be canceled out of the numerator and denominator because that coexists in those two, numerator and denominator. So that could be simplified by the uh, equal and the same term is canceled out of the numerator and denominator. So that should be limit x minus 2 in case the x goes to minus 3. So in that case, you just need to plug minus 3 into the x. That's in minus 3. Minus 2 should be minus 5. Okay. Also, let's take a look at the example number 2. Becomes more to become more familiar with this technique, dividing out technique. So the number 2 is to find out the value of the function f(x), which is x minus 1 over x cubed minus x2 x squared plus x minus 1 for the case x goes to 1. So we have to separate this the function in numerator, the denominator. So that case, limit x goes to 1, then x minus 1 over x minus 1 times x squared plus 1. So if you expand the denominator, then x minus 1 times x squared plus 1 must be equal to the x cubed minus x squared plus x minus 1. So there's a common term in numerator and denominator, so you can cancel them out. X minus 1 from those two positions, so that should be x the case of the main term in numerator and denominator, so that the numerator becomes 1 after canceling out of the x minus 1 term, and denominator should be x squared plus 1. And x now goes to the 1 or approach the 1. So all we need to plug the 1 into this function. So that should be 1 over 1 squared plus 1, which is 1 over 2. That is answer for this problem. So next technique is rationalizing technique to solve the limit case of the function. So still we need to take a look at the example problem to find out how this rationalizing technique works. So the example number 3 is we want to find out the function f(x) square root x plus 1 minus 1 over x in case x goes to 0. That is square root x plus 1 minus 1 in denominator, and numerator is, the numerator is square root x plus 1 minus 1, and denominator is x. So in this case, we have to actually just convert these two terms out of numerator and denominator with the additional multiplication. So we kind of like rationalize the this two numerator and denominator terms, so that help to actually add the x value into the given modified formula or function. So now we want to actually multiply convolution actually term to numerator and denominator of the x square root x plus 1 minus 1. So if you do that, that should be at limit, in case that so limit x square root x plus 1 minus 1 over x times square root x plus 1 to numerator, same term should be multiplied to denominators. So the x square root x plus 1 should be multiplied to the original function, and we want to find out that value of those modified function in case the x goes to 0. So you multiply this additional numerator and denominator term, sort of like rationalizing this function by multiplication of the same convolution term in the numerator and denominator, then that should be limit. X goes to 0, and numerator is the x square root of x plus 1 square minus 1 square. Denominator is x times square root x plus 1 plus 1. So this first term in numerator is same as x plus 1. And you have second term, but with the minus sign. So 1 can be canceled out of the numerator. Only leave the x term. So that should be limit x goes to 0 and x over x times square root x plus 1 plus 1. So the numerator, both numerator and denominator has the common term x. So that could be canceled out each other. That could be canceled out from numerator and denominator. So in that case, the remaining term is 1 of square root x plus 1 plus 1. And we want to find the value of that function in case that the x goes to 0. If you plug that number into this formula, then that should be 1 over square root 1 plus 1 plus 1. Now this first term equals 1. So that should be 1 over 2. That is the technique with the rationalizing the numerator and denominator. And now we're going to take a look at the next technique. So let's take a look at the other technique to find out the value of limit case. So I'm going to change the color of the pen. So using technology, so first case is the one-sided limits. If the f(x) function has different value depending on which fraction x actually approaches. So we need to take a look at that multi-solution case with the limit. So one-sided limit. So if the function becomes L in case the x goes to minus c, so that x value approaches c from the negative direction. So in that case, f(x) becomes L1 as x goes to c minus. So that's actually x approaches c from the negative side. Then that is called the limit from the right. And if function f(x) has another value at L2 in case x approaches c from positive direction. So in that case, f(x) becomes L2 in case of x is replaced with the c from the positive side. So L2 as x goes to c plus or c plus. So the x actually approaches the c from positive direction. So that is called the limit from the right. So we can actually visualize this idea. So you have the fx defined in the x-axis, and c is the target value x approaches. So if the function fx comes into the this x approach to c, then fx has L1, and if x approaches c but from the plus direction, then fx has L2. So the limit case of the fx function could be different, could have the different value depending on which direction that the x value actually comes from. So if it comes from the negative direction, that limit from the right, oh, actually, this one should be not, this one should be left. And the fx function has L2 in case x approaches c from positive direction, then that is called the limit from the right. So let's apply this definition to the example problem. So example problem number 6. So if fx is absolute of 2x over x, then let's take a look at the value of the this fx function in case x goes to 0. So there are two. I think that this similar problem already mentioned before. So in case x negative value, then absolute 2x should be same as minus 2x. So in that case, fx becomes minus 2x over x. So that is should be minus 2. And same thing, if x comes from the positive direction, then fx becomes 2x over x, which is 2. So the two value possibly exists at x equals 0. So there's discontinuity is possibly existing. So if limit x approach 2 from minus, I'm sorry, the x equal approach 0 from negative direction, then that should be absolute value 2x over x, the same as limit x goes to the 0 from minus axis, minus infinity, and that should be 2x over x, which is 2. And if x approaches 0, but from positive direction, positive infinity, so in that case, x, numerator should be the minus 2x, and denominator is x still. X goes to the 0 from positive direction, so that should be minus 2 times limit x goes to plus. So that's x over x, that is 1, so that's minus 2. So when x value, x actually approach certain value from different direction, in a positive direction and negative direction, or positive infinity or negative infinity. And the function fx has different value at the boundary of the boundary of that value given in the limit case. So that does not have the solution, right solution. Solution does not exist for the case that fx function has two different number at the same spot, x value. So there's a way to actually check the limit exists or not. If fx is the function and the c and l are the real numbers, then the limit of fx becomes L for x goes to c if only if both the left and the right limit exist and they are same or equal to L. So if there's discontinuity of fx values when x approaches to a certain boundary value from negative infinity and positive infinity, then if there's a discontinuity, then that the fx does not have any solution in the limit case. So basically, the L number should be same for the case x comes from positive direction or negative direction. Only solution can exist in case that x the value from negative infinity or positive infinity makes same at the numbers at boundary condition, and at x value equals a c, that's actual boundary spot. Okay, so let's take a look at the example, and that will help us to find out how limit can exist and what criteria could be applied to make judgment that if the fx has limit or not. So if you look at the example of problem number 7, then it will give you a more clear idea how we can actually figure out whether limit exists or not. So number 7 is defined by the function fx, which is 4 minus x in case x smaller than 1, and 4x minus x squared in case x larger than 1. So you plot that, it should be like this. Below the number 1 of the x, the fx is a linear function like this. So the value of fx at x is 4, x is 1, is number 3. And if in the range x is larger than 1, the function fx is parabolic curve like this. This one is 4 minus x, this one is 4x minus x squared. Same thing, as you can see, 4x minus x squared is the 3 in case x is 1. So at x is 1, two different type of function are equal. So we can actually take the limit out of this function. So let's take a look. If limit of function fx, the case x goes to 1 from minus infinity, then that is limit x goes to 1 minus 4 minus x. So that same as 4 minus 1, that is same as 3. If we look at fx from the direction out of the positive infinity to the 1, then now we have add the 4x minus x into the fx in the limit. So that is 4x minus x squared. Then x goes to 1 from positive infinity in the positive direction. So that is 4 times 1 minus 1 squared. That is same as 3. So as you can see, the value at boundary between these two functions types are same as 3. And next one, we can actually define, we can actually just find out the definition of calculus based on the limit, concept of the limit. Let's take a look at the example 9 to understand how the limit is used to justify the calculus, especially derivative. So we'll just have a chance to look at more, closely at definition or of calculus, derivative, and integral in the future. But let me quickly show you the example 9 to describe the basic concept of the calculus based on the limit. So example number 9. Fx is defined by square x minus 1. Now we have to find the limit of fx, but with this condition, fx with the x is 3 minus h minus f3 over h in case x goes to, oh, not x actually, h goes to 0. So that is actually basic expression. It's similar with the how derivative is defined. So let's take a look at how the function, what value that function has in case the h goes to 0 with this basic description of the derivative. So the first step is plug the x squared minus 1 into the equation of the limit over h. At h goes to 0. Now that is the limit h goes to 0, and 3 plus h squared minus 1 minus 3 square minus 1 over h. So if you fully express it, then there should be limit of function fx for h goes to 0. That is, the numerator should be 9 plus 6h plus h squared minus 1 minus 9 plus 1 over h. So 9 can be out of this numerator, and 1 also can be cancelled out, and that lead to the limit the function for h goes to 0, and numerator 6h plus h squared over h. So you can actually take the h out of numerator and denominator, and that should be the like limit h goes to 0 plus 6 plus h. Now you need to plug h into the bracket. So if you plug that 0 into the h, then that should be 6 plus 0. That answer is 6. So this shows how the definition of derivative works in case that the function goes to a certain value. So we will take a look at this definition later on, but this is the essential part of description of the derivative. So we will just stay with this expression of the derivative using the limit expression. I mean, symbol of limit in the future.